lunch. So please prepare for 3 lectures in a row. And the first lecture you will meet here on our summer school is Dr. Rostyslav Hryniv. He is a professor here in Ukrainian Catholic University, and as well he teaches in Rzeszów in Poland and in Lviv Ivan Franko University. So please welcome Rostyslav.
Thank you for this kind of introduction. I'm glad to be here in front of this great audience. Well, as you've seen, I'm Rostyslav Hryniv, and to start with, I'm going to disappoint you. I am not a DS, which stands for data scientist. Who am I? I am a BM. Any ideas?
Business master.
I am not very big. This stands for boring mathematician. Okay, so why I'm here today? Well, I consider my mission twofold. The first one is that if you manage to survive my 4 lectures, then all the other lectures will be just a toy for you. So that will be kind of survival test for you. Well, the other one is that I'm going to give you a very soft, mild introduction into the data science, of which I know nothing, yes, and machine learning related things. Mainly during these 4 sessions, we'll try to recall the basics of probability theory, which is actually very basic, very vital for the whole data analysis science. And then we'll discuss parameter estimation, because this is a task which often occurs in data analysis. We'll introduce the main, okay, so it's not the main tools, but the main tools in statistical, of hypothesis testing, and finally learn, or maybe recall again to some of you, some regression models. Okay, so as I told you, I am not a DS. So what, in your opinion, is data science? Well, this is my definition. It's an art of making money out of meaningless information. Well, in other words, it produces an extra added value to the data we have. That's like a car plant. Yes, in input you have piles of metal, plastic, wires, and etc. And the output is a car, modern car. Okay. Of course, the cost of this car is maybe 100 times or even more larger than the cost of all the ingredients. Okay. So, in a similar fashion, data science produces an added value to the information we have. Well, while in the car industry, the main tools are very complicated equipment, which does all the things. To my opinion, in data science, the magic tools are probability and statistics. And I'll give you 2 small illustrations to this point. So here is an example of meaningless information. It's indeed meaningless because I just simulated it artificially. So X and Y stands for nothing. Okay, but with very little effort, I'll do the following thing. I'll go to my RStudio and make this. Just draw this red line. I assure you that the cost, the price for this picture is several times larger than the one without them. Okay? Well, even more, there are some more analysis which I just performed by just one click. There are some words, some notions, some numbers, and the idea is that you should at least understand what these numbers are for, what they mean, and be confident in explaining the picture you see. So, for instance, now after this red line is drawn, you can argue that given this data, we can infer that increasing x, which can stand for at least, for instance, the qualification obtained or whatever, should result in increasing y, which could be a salary, for instance, on a certain amount. Okay, another example I was going to give you is the following. How many of you are still student or are going to be students? Okay, quite a lot, thanks. So here is some example of using probability for increase your grades. Okay. In our national system, Ukrainian national system, the grades are from 1 to 5. 5 being the best one, not like in Germany, where 1 is the best. Okay, so the mean of these 5 numbers is 3. So 3 is an average or expected value of these grades. So you can approach your teacher even before the exam and try to convince him or her that, okay, you see, 3 is the expected value. So I expect to get at least 3, and you expect that an average student will get 3. So let's make a deal. Let's just fix it at 3. Okay, and if you are not an average student, which all of you, of course, are not, yes, then you can argue even further and try to bootstrap between 3 and 5, and guess what your grade should be? Okay, so with very little effort, to sound more confident, you can use confidence intervals or stuff like this to gradually convince your teacher that you are probably worth the whole 5. Okay, so that was a kind of joke. And now let's start our first part, which will be about probability theory. Okay, probably most of you, or maybe all of you, had probability in your university. Yes, but still, maybe it's worth recalling some basic notions and playing some games. There will be several games, so be patient. Okay, so what is probability? Well, whenever we are not sure of something, we apply probability. We say that there is a probability, or some things are likely or more likely than others. And in very naive sense, we define the probability of some event, random event A, as a value of the chance that this event happens. Okay, well, this requires that it should be possible, at least in theory, to repeat the procedure, the experiment infinitely many times under the same conditions. Okay, and then one expects that this probability P of A becomes close to the frequency of the times of occurrences of A in this series of n trials. That's why there is no probability for an event that the moon will ever fall on the Earth. Well, because if it does, then probably there is nothing left of the Earth, and you cannot perform this experiment for the second time. Likewise, there is no probability that Donald Trump will become the next president of the United States. Not because this will be the end of the United States, but just because this can only be run twice. Okay? So, anyway, historically, the source of repeated experiments came from gambling, where the people were sitting, drinking beer, throwing coins, or playing other hazard, playing other games. So this was indeed a fertile soil for questions of winning strategies, and although the intuitive definition of probability we gave before do have some grounds. For instance, this is based on the so-called law of large numbers, but a very elegant theory was created only in the 30s of the last century by Kolmogorov. And the classical definition of probability reads as follows. So assume we have an incompatible elementary and equally possible events, which we denote by omega 1, omega 2, omega n. And then the probability of an event A is equal to this ratio, where this sharp A stands for the number of elementary events in A, and n is the total number of events. So that's very, very simple. For instance, the simplest random experiment is throwing a coin. So I have a coin. Actually I have two. They totally cost £1, but it's becoming worthless after Brexit. Anyway, so if I flip the coin, then there are only two possibilities can rise, unless I lose my coin, of course. So either head, do you see the head of the pin, or tail? Okay, so head or tail. There are only two possibilities, and because this coin looks perfectly symmetric, we expect that both probabilities will be equal to 1/2. They should add to 1. We'll say about this. Well, actually, there are only two events, omega 1, omega 2, and the event A is that the coin returns head. Therefore, according to this formula, the probability is 1/2, so 1/2. Okay, now I have another coin, and I flip these two coins and try. Okay, so there are only 3 outcomes possible: 2 heads, 2 tails, or 1 head, 1 tail. Therefore, the probability of getting each of these should be 1/3, right?
No.
No. Why not? Well, because I've cheated. These coins are not identical. Here you have Peter Rabbit as a tail, and here are another emblem. So they are indeed distinguishable. Therefore, this and that events are not equal, are not the same. Okay, so in fact, here we have 4 outcomes: head, 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 tail, tail, head, and 2 tails. And now we can argue that all 4 of them are actually probable. Therefore, each of them should have probability 1/4. Well, that's very simple, but already here we notice that a very logical statement actually are sometimes wrong. For instance, that was a long-standing paradox why throwing 2 dices produce more likely 7 points than 6 points. Because one can argue that 6 points we get only in, so what are the events leading to getting 6 points in rolling 2 dice? So 1, 5, 2, 4, 3, 3, okay? And likewise 7 we can get by as 1, 6, 2, 5, 3, 4. But in fact, because 2 dice, okay, I have a dice here. Very small one, little one. Because 2 dice are actually distinguishable, as in the case of my quiz, actually it is very easy to understand why these 2 probabilities are not equal. There are other reasonable but false statements. For instance, let's consider the following one. Assume I have 3 coins. Well, I have only 2, but anyway. And you flip them. Then at least 2 will show the same face, either head or tail. Then the third one with equal probability will return head or tail, and with probability 1/2, this face of the third coin will be the same as that of the first 2.
No.
Therefore, the probability should be 1/2, yes? But that's not the true. The probability is actually 1/4, just because you have 8 elementary events here, and only 2 of them getting 3 heads and 3 tails will lead to the success. Well, there are other subtle things. For instance, another approach to probability, to defining probability, is a geometric one. If we have a device which chooses randomly, here randomly means with probabilities only dependent on the area of a subspace. So we have a subset here inside. This is A. The big is omega. And then we define the probability of A as the measured area of A over the whole area, given the assumption that we pick every point with equally likely, in the sense that the chances to pick a point in a subset only depends on the area of this subset. But even here, there are known paradoxes, like very well-known paradox of Joseph background, and it goes as follows. So assume you choose randomly, at random, 2 points on the circle. Okay? So I have a circle, and I choose 2 points at random. Say, that one and that one. Well, now we draw a chord and are interested in probability that the length of this chord is at least equal, or maybe larger, than the length of equilateral triangle inscribed in this circle. Well, it turns out that the probabilities of this event might be equal to 1/2, or 1/3, or 1/4, depending on your preferences. So actually depending on how you choose these random points, because there is no specific algorithm, specific procedure described how do we choose these. Okay. Well, we have already seen that even in simple situations, many events, some events which seems pretty the same, yes, got different probabilities. So in order to meet these, Kolmogorov suggested the following definition, very abstract definition, but we will have examples in a second. So he defined the probability space as a triple composed of three objects. The first one is very abstract sample space, elements of which are elementary, so-called elementary events. They are, for instance, the collection of all possible results when rolling a dice twice that are elementary events, or tossing a coin n times can be considered as elementary events. This F is a collection of all some subspaces called events. So, in addition to elementary events, we can consider some composed events. For instance, rolling a dice twice gives 7 points is certainly a composed event when we throw the dice twice. Or there are 2 heads in 3 tosses of a coin is also some event which should be in this collection F. And finally, there is a probability P which assigns a number P of A between 0 and 1 for every event in this collection. There are some very clear, intuitively clear properties of the probability. For instance, if P of A is equal to 1, then we are certain that A occurs. And if P of A is equal to 0, we consider this A as an impossible event. Then this probability, this measure, should enjoy the addition property, additivity property, if A and B are incompatible or disjoint, meaning that they don't contain joint elementary events, so their intersection is the empty set, then the probability of the sum or of the event that either A or B or both occur should be equal to the sum of A and B. In fact, similar equality should also hold for a larger number of summands. From these, we automatically get that the probability of a complement, that is negation of A, is equal to 1 over P of A. Even more, actually, if the events A and B are not incompatible, so they do have a non-empty intersection, then we can easily derive the following more general summation formula, which takes into account this common part. And intuitively, it's very clear because while adding PA and P of B, we count common elements twice, both in A and P, and therefore we should subtract it. Okay, here is a very simple example. We roll a dice. Then omega is the collection of six elementary events, because, well, at least my dice is perfectly symmetric, so I should give no preferences to one face over another, and therefore the probability of each of these elementary events should be equal to 1/6. If A and B denote the event that the number of points is even or the number of points is multiple of 3, then A is just omega 2, omega 4, omega 6. B is omega 3, omega 6, and we easily calculate that the probability of the sum is 4 omega 6. Very important notion of probability is independence. Well, we call 2 events A and B independent if their probability obey this rule. So if the probability of common part of A and B, so the probability of observing A and B simultaneously is just the product of 2 probabilities. It's probably not very intuitively clear, but still it works, and it agrees with our basic examples In particular, if we have two incompatible events, so if the common part, the intersection of A and B is the empty set, then we have 0 on the left-hand side. Therefore, the only way is to get 0 is that either A or B should be impossible. Okay, that's clear. So, contrary to our maybe intuitive understanding, incompatible events are not independent because occurrence of A already rules out the possibility that B occurs. Okay? So there is clear dependence. The events, the impossible and sure event are independent of any other just because we have either 0 or 1 as one of the factor, and that's it. Okay, well, let's consider this toy example I started with tossing 2 coins. Then, as you already know, the probability space should contain the sample space should contain four elementary events. This collection of all events should be composed of all possible subsets of omega. We have this special notation 2 to the power omega to indicate that, including at the empty set in omega. And P is defined by the following formula. This means that we have a bent coin, and probably the probability of getting head is not equal to 1/2, but it is some number P. So if we define the probabilities of these 4 events this way, then the probability, the event A, which means that the first toss returned head, and the probability, and the event B, which is the second toss returned T, are composed of two elementary events. And we can easily calculate the probability of A and B and the common part, the intersection of A and B, and we observe that the necessary definition equality holds, so these A and B are independent. Of course, it's possible to generalize this to infinitely many, or finitely many, tossing of the coin. So the only cumbersome thing is that probability of an event omega here is equal to these products of p's. The number of these products is equal to the number of heads occurring in these sequences, and q to the respective power. And if we define this probability this way, then we can check that the outcomes of the different tosses, the first, second, third, and so on, are pairwise independent. Well, that's clear because our coin doesn't have any memory. There is no memory chip inside, at least I hope. Immediately after we have tossed it for the first time and tried to toss it the second one, it remembers nothing of the past. Therefore, sometimes it's counterintuitive that irrespective of how many heads in a row we got, the outcome of the next one, of the next toss, will be probability will be equal to 1/2 of getting head and tail. So even if we have managed to produce, say, 5 heads in a row, the 6th one will turn up head or tails with equal probability. Well, let's check your intuition. Assume each of you have tossed a fair coin, this one for instance, 100 times. What is the largest run, H run or T run you should expect? I mean, what is the largest possible number of heads you got in a row, or tails you got in a row?
100.
No, I mean, well, you are very optimistic. The probability of this particular event is 1 over 2 to the 100. I mean, what a typical number is. Not expected, a typical. What you expect will be, if you do this, how many heads in a row or tails in a row at largest should you expect?
1.
Oh, well, 1 is certainly not,
So
because
that's 2 times more probable than 100.
once again, please.
1 is only 2 times more probable than 100.
No,
Because
I don't think so. Anyway, well,
About 5
give me a
times.
number.
5 times.
5 times.
17.
Oh my God, you are lucky. Well, let's run simulation. Okay. So I have thrown. Okay, I can somehow enlarge this. So I have tossed the coin 100 times. Okay, this is the outcome. Well, this is just a sample from the binomial distribution with equal probability 1/2, 1/2. Okay, so now what I do, well, as you've seen, as you see, there were 48 tails, heads, and 52 tails. So we are pretty close to half. And the longest run is 7. Probably you can even detect it, but anyway, believe me, it's 7 here, somewhere here. We have maybe here. Yeah. We have 7 zeros in row. Okay, let's do this one more time. So it's 13. Oh, very close to 17, but it's already 13. It's counterintuitive that while throwing only 100 times, we managed to produce 13 heads or tails in a row. Okay. Good. Good. Well, we can of course generalize the notion of independence to not only 2 events, but to finitely many events, and call them independent if any subset of, or any subset of them, the following quality holds, but that's maybe pretty technical and is not very important at the moment. Okay, now we move on to a very important notion of conditional probability. Well, usually we do have some information. It might be insider information, then you're lucky, you can be fortunate. Stock exchange. But in any case, assume we already know that some event has occurred. So, given it, we can review our beliefs on chances that some other event, A, should occur, or could occur. Namely, if A and B are incompatible, then we already know that only one of A and B can occur. Okay, so if B occurred, then A has no chances to occur. So its conditional probability will be 0. On the other hand, if A contains B, then we know B occurred means that some elementary event, or at least one elementary event inside B has occurred. But this elementary event is also in A because A is larger. Therefore, A automatically must occur. Therefore, given that B occurs, we know that the probability of A, of occurrence of A, is 1. It's certain under the condition, given the condition that B occurs. It's very vital in probability and many other areas of mathematics and applications, because very often we gain some extra information in the process of research, and we should constantly review, modify, so to say, update our beliefs, our theories. Okay, so let's recall the formal definition of the conditional probability. So the conditional probability of A given B, denoted this way, is equal to this ratio. Well, it's again very clear from geometric interpretation. If this is B and that is A, then because we know that B occurred, only those elementary events of A which are in B have chances to occur, and therefore the probability of this, given that B occurred, is proportional to the part of A which is in B. And so that's this number in the numerator, and the denominator is needed to make this number, make the probability, to norm the probability to 1. Okay, observe that this family with fixed P of dot B with fixed P is a new probability on the sample space, restricted to B, and that the conditional probability of A given B is equal to the original P of A if and only if A and B are independent. Well, of course, if A and B are independent, then the information that B has occurred doesn't influence in any way chances of A, because A doesn't depend on B. So that's clear. Okay, so a very simple toy example. If B is the event, there was just one head in 3 tosses of the coin, and A is that the first toss returned head, then the intersection of A and B is just this one elementary event in the corresponding probability sample space, because this is indeed just one head in 3 tosses, and it is on the first trial. On the other, B consists of 3 elementary events, and we can calculate the probability of the conditional probability of A given B as 1/3, irrespective of what P and Q are. So, original probability of getting head of the first toss was P, but the conditional probability, given that we know that there was 3 tosses, and that there was just one head in 3 tosses, is 1/3. So we see that this conditional probability is quite different from that of A. There is a very important consequence of the very definition, which is called the probability product rule. And we can calculate the probability of the common event A and B as in this funny way. Well, although this seems more complicated compared to the original event, in many cases we do have conditional probabilities and can easily use this formula to calculate A of B. Generalization of this is the probability product rule for n factors, which reads as follows. Here, just I omitted the cap sign for the sake of simplicity. So this product means the product in the theoretical sense. So is the joint common part of this. Well, here is an example. Assume that urn contains 2 black balls and 3 white ones. 3 balls in turn are drawn randomly without competition, so you draw and put them aside. What is the probability that all of them are white? So there are just 3 balls, we draw 3, and wonder if we can hope for a lucky chance to draw all white balls. Well, if we denote by A1, A2, and A3 the events that the respectively first, second, and third trial returned white ball, then we can easily calculate the probability of P of A1, P of A2, and P of A3, and the probability of the common part. So this is exactly the probability that all 3 drawn balls were white, using the probability product rule, indeed. So this is just the first factor. There are 3 white balls out of 5, so the probability is 3 over 5, 3/5. Then after the first have been drawn, there are only 4 balls, 2 of which are white. So if you choose randomly, then the probability to get second ball white, given that the first drawn was white, is 2/4. And likewise, the probability that the third one is white, given that the first 2 were white, is equal to 1/3, because there are only 3 balls left and only 1 is white. Therefore, this probability is 1 over 10, 1/10. The next 2 things, we are very close to the end actually. The first, this formula called total probability rule allows one to calculate the probability of A given the conditional probability of A under B case, where B is some partition of the sample space. Well, I don't expect you to memorize or to understand even these formulas. Just for the sake of so to say, just to revive your knowledge in probability. This is, and well, here is an example of application of this formula. We would like to calculate the probability that the second ball drawn is white, regardless of the first one. Well, it's clear that the first draw will result in a white ball with probability 3/5, because there were 3 white balls and 2 black ones, therefore 5 altogether. 3 are lucky, so the probability is 3/5. It's somehow surprising that the probability that we'll get a white ball during the second draw is also 3/5. The probability that the third ball drawn will be white is 3/5. Could you guess what is the probability that the last drawn ball is white?
The last.
Yes, the last one. 3 or 5, sure, 3 or 5. What else could it be given this information? Okay. Well, and also there is a very nice thing called bias formula, which allows one to calculate the conditional probabilities of some event B given A if we know the reverse conditional probabilities. That is, conditional probabilities of A given some set of events. So this reads like follows. We have some partition of the sample space, so n incompatible events, which are the union of which is the whole omega, and then if provided that we know the conditional probabilities of A given Bk, we can calculate the conditional probability of any Bk given A. Oh well, let's try to use this for the following situation. So assume that an urn contains one ball which is white or black with equal probabilities. So I have two balls, white and black. I choose one and put it here. So here is the second one. I don't know which color it is. And I put an extra white one. So now I have two balls. Okay, believe me, there are only two here. Two balls. One is white because I just put it there. And the other is either white or black with equal probabilities because there is another one. Okay, so I draw one of them at random and it turned out white. What is the probability that the remaining ball is white? Well, it is either white or black. So 1/2. No. Well, let's check if I am lucky. Ha! Here I am. Well, actually, the probability is 2/3. That's why I was pretty sure that I will get the second ball white. So, not cheating here. Why is this so? Well, it's because the bias formula tells us. You can revive, well, actually, we have B and complement of B as a partition, and we use this in this bias formula. And believe me or check this calculation at your leisure, that the formula gives you 2/3. Okay? Here is a similar game. I have 3 tokens. 1, 2, and 3. You notice they are of different colors. One is green on both sides. One is rose, or what's pink? Okay. On both sides, and the third one is mixed. Okay, I put them into my wonder tool and draw it at random. And you see the color here is purple. So the other side can be either green or purple or pink. Pink, okay, pink. What are the probabilities of both these events? I bet on pink. Just for fun. It's 1/2 anyway. Okay? Okay, 1/3 is not a very big probability so not very small probability. Actually, the probability of getting both sides of the same color are again 2/3. Well, 1/3 probability of losing is not very small, so I was lucky the first time, but I lose the second one. You can try to prove this using the same bias formula. So I just invite you to do this. Well, there are several other examples, but you'll get these slides for your review, so you can read them and try to understand. Okay, actually, it's not the random events the probability theory is interested in. It's rather random variables. Because you see, an event is not just abstract. So usually the event is not just an abstract random event, is not occurring just for fun. Sometimes it brings some gains, financial gains, for instance. If you knew what would be the exchange rate, for instance, tomorrow, you'll certainly benefit from that. Or if you bet on some sport events, for instance, if you bet on France, then of course is it random? Anyway, let's assume the probability is 1/2 for France to win. Then of course, if you lose, then you lose your stake. If you win, you'll get some extra thing. So actually, very often, events come with some values prescribed to them. Well, a very simple example is if we throw the coin n times and count the number of heads. Then each elementary event, that is the outcome of n throwing, will produce you some number, which is the number of occurrences of heads in this series. Okay? So in this particular example, that random value, that random number of heads in a series of n trials, can attain n+1 values ranging from 0 to n. Okay? And if p denotes the probability of getting the head in one toss of the coin, then we know that x is equal to 0 only for this probability, for this event, and therefore we can calculate the corresponding probability that x is equal to 0. X is equal to 1 for n different elementary events, namely this unique head can occur during the first toss, the second one, and so on. And therefore, generally, we can calculate the number of events with exactly k heads as these binomial coefficients, so this number of combinations of k elements out of n, and therefore the probability that x obtains the value k is equal to this one. This is the probability of each of these events times the number of these elementary events which constitute this event. Okay, so we can convince ourselves that indeed these probabilities sum up to 1, so it's probability distribution, so to say, so it's the probability on the space omega. And actually this x is an example of a random variable that has binomial distribution. In general, how do we define the, so we can calculate the expected or the mean value of x by this formula. And in this particular case, we can group first all events for which x of omega is 0, x of omega is 1, and so on, and calculate the probability of the expected value of x to be n times p. And it's quite intuitively clear then, because what is the probability p? It's an average number of heads we obtain in one toss. It's proportion, so it's k over n, where k is the total number of heads. Therefore, this p is just the fraction of heads for one toss. Therefore, the expected value of x after n tosses is n times p. Well, if we have a random variable that is the function of omega, which takes values x1 to xn, the probability is p1 to pn, then we define the probability, the expectation or expected value of x by this formula, and that's the particular case of this we had just before. And also we introduce the variance of the random variable x to be the expected value of x minus mean x squared. So it's the measure of how far x is distributed around its expected value, its mean. Okay. Well, there are random variables which assume only discrete values, like the binomial distribution, and those with continuous distribution. For our binomial distribution, we can calculate the variance actually, so recall variance is this, and it can be calculated as the expected value of x squared minus square of the mean value, and the calculation gives that variance of x is npq. This will be needed later on. So here is another example of a random variable containing only finitely many or countably many values. That's the so-called geometric distribution. If we take a coin and repeat tossing it until the first head occurs, it's not a head, it's tail. So how many tosses, okay, on average, or how many tosses should we or can we wait until the first occurrence of head? If you are lucky, then this head will show up on the very first travel. The probability of this is the probability that y, the number of tosses before the first head shows up, is equal to 1, is just p, because we know that's the probability of tossing a head. If we have to wait n times before the first occurrence of head, this means that the previous n minus 1 tosses were tails, and the probability of this is just the probability of this elementary event, and our model, it is q to the n minus 1 power, because there are n minus 1 tails, times p. And one can calculate the expected value of y, so expected number of tosses required to get the first head in the following way. So, okay, here is some analysis, but anyway, the answer is 1 over p, which is also intuitively clear if we have only p fraction of a head in one toss. How many tosses should we make to get the whole head? 1 over p, of course. Okay, so it's intuitively clear. Well, we already tested your probabilistic intuition on this question. You were lucky to get 17, and I got 13 heads or tails in a row on the second attempt. So that's really amazing. Well, finally, a few words about random variables. These were, of course, a kind of toy examples with all these coin tosses, etc. In reality, most of the data we have are not integer. They can contain any number. For instance, your salary or future salary after graduating from this summer school will probably be very, very large, but never negative. Okay, so potentially it could be anything from 0 to infinity, excluding 0. Good. we have a very simple example of a random variable assuming all values on the interval between 0 and 1. If we just call the random number generator, which returns a number between 0 and 1. Well, it's not any number because, of course, we have limits on digits, but anyway, it's pretty any number between 0 and 1. So that's an example of a random variable drawn randomly. So the value is drawn randomly, and this value is anything between 0 and 1. Another very important example will be the normally distributed random variable. I will turn to this later. But if we have a random variable which can assume any real number, then we introduce several notions. New notions, probably it's probability or cumulative distribution function measures the probability that that x assumes values less or equal to t. This is a non-decreasing function tending to 0 at minus infinity and to 1 plus infinity. So x is a discrete random variable if this cumulative distribution function is a step function. I'll show you some pictures later on. But x is called continuous if its cumulative probability distribution function is small, it's differentiable. So, roughly speaking, this function f is the integral of some other function, little f, and this little f is density of x. So, given this, we can calculate the probability that x assumes values in any interval delta as this integral, and in particular, our expectation can be calculated as just this integral t times the density function, and the variance is this integral t minus mean x squared times the density function. Here is an example I already mentioned earlier. It's a uniform distribution on an interval AB. That's a random number generator on the interval AB, which produces such a random variable. Then, because it's equidistributed on this interval, its density function is constant on the interval from A to B. And to meet the normalization, we have to assign the value 1 over B over A on this interval and 0 otherwise. Okay, and here are some calculations of the expected value, which is A plus B over 2, which is also clear because this is the mean value of this interval. A is the minimal value, B is the maximal, therefore the mean value is exactly in the middle. Okay, and with some calculus skills, we can calculate the second moment, that is expectation of x squared, and the variance, which turns out to be this one. Well, there is another way to calculate these things. If we represent this x in terms of the standard uniform distribution on minus 1, 1, but again, these are some details. And here, the second important distribution, which is the standard norm or Gaussian distribution. It's given by the following density function of this form. It's easy to understand that this function is even with respect to the origin, therefore opposite values are taken with equal probabilities, therefore the mean value is 0. And again with some some skills, calculus skills, we can calculate that the variance is equal to 1. The variance in this case is just the second moment, because as you remember, the variance is a difference of the second moment minus square of the first moment, so minus x squared, but it is 0 anyway. Good. Well, actually, this was the standard normal distribution. We'll denote this by n 0, 1. 0 is the mean value, 1 is this variance. But more generally, we have the whole family of normal distributions with two parameters, me and sigma squared. And not surprisingly, this me stands for the expectation, and sigma squared for the variance of this variable. We can derive the density of this random variable. It is this Frieden-looking expression. Actually, if sigma is 1 and me is 0, then we get the previous value. Okay. Another example is the so-called exponential distribution. It's again also very important distribution in statistics, because many real-world phenomena are modeled with the use of this distribution. Okay, so it's a distribution with this density, which is e to the power minus lambda x times lambda for positive lambda, and 0 as for negative axis. So it's a random variable which, roughly speaking, describes the time, random time you have to wait until some event occurs. For instance, on a bus stop. Well, very often there is a timetable, but very often it has nothing to do to the real schedule. So if you come there, then you'll be interested in how long do you have to wait until the bus comes. And actually, the distribution of these times approximately is given by this exponential distribution. For this x, the expected value is 1 over lambda, and the variance is 1 over lambda squared. And remember, we talked about independent events. Similarly, we can introduce the notion of independent random variables. Roughly speaking, we call two variables independent if any events of this type. So the event that x assumes values less or equal than little x and similarly for y are independent. Well, it means that because these two events are independent, therefore this formula should hold. And in terms of the joint cumulative distribution function, it results in this expression, because roughly speaking, these f's here, and there are precisely the probabilities of these events are precisely the values of these functions. Anyway, in terms of the density functions, we have this expression. So if x and y are continuous, so possess density, then the generic density is equal to the probability. Anyway, if x and y are two random values, then it's very easy to understand that the expectation of the sum is the sum of the expectation. However, this is no longer true for variances. The variance of the sum of x and y need not be equal to the sum of the variances. Why? Because if you take, for instance, y equal to minus x, then here is 0, and the variance of 0 is 0 because it doesn't vary at all. 0 is constant. So you'll get 0 here and non-zero there. So it is not going to hold for all x and y's. However, it does hold for independent random variables. That's why independent random variables are important, because, for instance, the variance of their sum is the sum of the variances. And, okay, here is, again, an example. So, let x have binomial distribution, and we already know what it means. It's the number of heads, for instance, in a series of n tosses of a coin. If we take p arbitrary between 0 and 1, it means that my coin is bent. It is not symmetric. I tried to bend this one, but still, England is still very, very safe, so to say. At least their coins are hard cards. Good. So, how can we represent this x? Actually, we can represent it as a sum of the following indicator random variables xi1, xi2, and so on, xn. Xi1 is an indicator of success in the first trial. It means that it assumes 1, the value 1, if the first toss returned head and 0 otherwise. Similarly, xi2 is equal to 1 if and only if the second toss was head and it's 0 otherwise, and so on. So these xi are indeed indicators of successes. If we regard head as a success, then the total number of successes is just the sum of the number of successful trials, and these xi's actually pick the successful trials. Okay, so the sum of these xi's is exactly the total number of heads. So we have this equation, and the xi's themselves have very simple distribution. It's again binomial distribution, but with n equal to 1, and therefore it's very easy to calculate the expectation and the variance. For instance, the expectation of xi according to our formula, it's the value 1 times the probability plus the value 0 times the probability. It's clear P. And similarly, the variance can be calculated to be PQ. Therefore, because we know that xi1, xi2, and so on are independent, because we proved that actually on the level of corresponding events. So, do you remember in our model, the event that the third toss was head is independent on the event that the second toss was tail, for instance. Therefore, these are indeed independent, and we can apply the sum formula for the variance, and observing that the variance of every summand is PQ, we reproduce the formula calculated earlier. Well, actually, the sum of the variances, the variance of the sum is equal to the sum of the variance. Variance is not only for independent random variables. That formula also holds for so-called uncorrelated random variables. The correlation covariance of x and y is introduced this way. If covariance is 0, then we call this uncorrelated. It's not the same as having x and y independent, but quite close to. Roughly speaking, what do we have here? If x assumes larger values than the mean of x, then y should sometimes assume values less than its mean. So there is no correlation. It's not the case that increasing x will result in increasing y, because then, roughly speaking, these two factors here would be of the same sign, and therefore their product would be positive, and the correlation covariance would be positive as well. Well, anyway, for uncorrelated random variables, we have the same formula for the variance, and actually that's the corollary of this more general formula for variance of the sum. So here we have this covariance here, and if it is 0, then of course the formula holds. Okay, well, we have 4 minutes. Time for game. I'll assume I have two envelopes. I don't have. Anyway, assume I have. So that's, here is 1 second. In one of them there is price, both x, and the second one contains the amount of 2x dollars. Okay? You don't know what is where, of course. You choose one of the envelopes at random, and then I know what is where. I give you an offer. I suggest you to switch your choice. Okay? Should you switch or not?
Depends on your intentions.
Well, it depends on your intentions, of course. I presume that you are interested in getting more, aren't you?
Not.
Okay, so I suggest you 2 solutions to these problems, depending on whether you are optimistic, are you? Or realistic? Okay, realistic. Well, there are 2 sums, x and 2x. If you choose smaller one and then switch, then you increase your gain by x. If you have chosen the larger one and then switch, you decrease your gain by x. This happens with probability 1/2. Therefore, it doesn't matter. Okay? Well, I should say that's a pessimistic, rather pessimistic point of view. I'll give you now the optimistic picture. Okay? So, now look at this as follows. There is, assume you have chosen an envelope and there is a sum y equal to y. Okay? Then the second one contains either 2 times y or half of y. Okay? Because one sum is twice as large as the second one. Now, let's calculate your expected being after you have switched. Okay? And assuming that your current envelope contains y, you can get 2 y's with probability 1/2 and y over 2 again with probability 1/2. So your expected value will be 2 y's times 1/2, which is y, plus y over 2 times 1 over 2, which is y over 4. And this sum up to 5/4 of y. So your initial value was y. After switching the envelope, you increase your expected value by 5 over 4. Why are you not happy? very, very interesting question. But now, let's change our mind and switch once again. So we have returned to our initial envelope, but by doing this switch 2 times, we have increased the expected value in 5 quarters squared. Isn't it a miracle?
That's what probability does for you.
Well, that's what probability does for us. So learn probability. It's quite useful in your life.
Increase
Okay,
the value.
time for a break.